If you want to check how much current your trolling motor is drawing, you can make yourself a current meter with a cheap battery monitor that you can get from Amazon. I'm putting this battery monitor, voltmeter, ammeter into a waterproof box that I got from there also, and running the power cables through these waterproof clan nuts. The result isn't going to be 100% waterproof because the meter itself is not waterproof, but when I put it into the box, I'll put some silicone caulking around the edges, and the only way that water should be able to get in might be through the display itself. It should be pretty splash proof. It probably wouldn't be submersible, but it'll be all right. I'm using 10 gauge wires to carry the power through the box. You have the positive wire that goes straight through. In this case, I put a break in it because I wanted to feed this wire through this gland nut, and I had already put connectors on the wires, so I couldn't go this way, and if this was continuous, it wasn't going to go through. So I cut it in half, fed it through from one side, fed it through from the other side, and then this is the wire that is the connection that goes between the positive end of the battery and the meter. So that one just jumpers straight on up. And don't be like me, an idiot, and use super short wires in here, because I did have the other connections that went from this shunt bar up to here, and they were too short. And that's what you can see here. I have this box open because these were too short, and they pulled out of the meter. I ended up out on the water to do some testing, and I couldn't measure my current. So use longer wires. Make it easier on yourself. I had cut some longer wires and brought them down to the garage to wire this up, but these though are a little small, not because they need to be large to carry current to this meter, because they do not. The wires that go to the meter can be very thin without a problem, but these are so small that the crimps that go to the screws that screw into the shunt are fairly large inside, and there was no way I was going to get a good crimp on these tiny little wires into this little terminal lug. So I'm going to use some larger sized wires just for the ease of doing the crimps. In this box I have a piece of 1/8 inch thick Lexan that is screwed into a couple of little screw posts that are built into the bottom of the box, and the resistor is attached to that Lexan with some through holes that go through, and these bolts are bolted through this piece of Lexan and up into the resistor. Then the main power leads that come through here, I have this connected the way that it showed in the diagram, using the resistor in line with the negative connection, so that my battery is on this side, the power flows through the red wire to the motor, and then back from the motor through the black wire to the positive side of the resistor, and that's why this red wire is on this side of the resistor. And then this is the negative side of the resistor, which is why these two black wires are connected to this side. You'll note that my heavy-duty 10-gauge wires are connected to the resistor with heavy-duty terminals. I made those terminals myself by taking an old copper tray that I got at a garage sale and cutting it up and making some little flag terminals that I crimped onto the wires and then soldered them and then drilled them so that it had the right size for your battery connections. And these are 5/16 inch diameter bolts. I didn't want to wait and order terminals that would fit onto here, but that's really the right way to do it. You could always just order them and crimp them on yourselves. If you're curious about why a battery monitor works the way that it does, and particularly why a shunt style ammeter works the way that it does, let me give you a short little explanation. It works on the principle of Ohm's law, which says that when you have a resistor, the voltage across that resistor is going to equal the current, which is I, times the resistance. And in this case, the shunt that is in this meter is rated. It actually has the numbers engraved on the side of this resistor, because that's what this is. They call it a shunt, but it's a shunt resistor. And really, it's just a big resistor of low resistance. The numbers that this is rated for, or that it's calibrated to, and you can see that it's calibrated by cutting a notch in the profile of this piece of conductive material that goes between the two terminals. The value of this is that the voltage drop across that shunt resistor is 75 millivolts for 100 amps. The reason that that's useful is that you can use that principle to have a resistor, and the symbol for a resistor looks like this. And if you have a positive terminal on your resistor, plus, and a negative terminal on your resistor, minus, you will get current that flows through that resistor in this direction. And when you do, if you measure the voltage right here with a voltage meter across this resistor, and you know what the resistance value is, when you measure this voltage, you can calculate the amount of current that's going through it. And that's exactly what a shunt style voltage meter does. What they're doing, they're taking a circuit. So if you have a battery, let's say that your battery looks like this, and it has a positive terminal and a negative terminal on it, and one way to hook it up would be to run it over to your motor. This is your motor with its load. The current would be flowing in this direction, and then the current flows this direction through your shunt resistor and then into the negative. So you've got your current flowing in that direction. And then if you measured the voltage across this resistor, that tells you what your current is. And for little semiconductor components, like what are in this meter, it's very easy to measure voltage. And that way the components don't have to be sized very, very large, because the thing that's carrying the high value of the current is this big shunt resistor. The semiconductors in your meter are not carrying that current. That's why the little wires that can go to this box can be sized small, but the heavy wires that are carrying the current in the circuit need to be sized large. So the way that I've drawn this is one way to do it, and it matches up with the diagram that's given here, where you've got a battery, you've got your positive current flow flowing out of the battery going into the motor, and then the shunt resistor is in line between that current path going into the battery. There are two voltage meters inside of this unit. The first one measures the voltage in the battery itself. So this one goes to the plus side, and then this line goes to the negative side. And that tells you how much voltage is in the battery. It also is what powers this little semiconductor unit. The other voltmeter in here is measuring the voltage drop across the resistor. So that one is hooked up to here, which is the negative side, and here, which is the positive side of that resistor. So that's why these connections are laid out the way that they are. You could also install this resistor not between the motor and the negative connection of the battery, but you could also put it between the positive terminal of the battery and the positive terminal of your motor. And in that case, that circuit would look like, so here's your battery with a positive terminal and a negative terminal. In that case, you'd come out, you'd go through your resistor, you'd come over to your motor, and then your motor would be directly connected back to your battery. And now your two voltage meters, you would have one that would be measuring the voltage across the battery itself. So you'd have terminals that came to here, call that V, voltage of the battery. Boop. And that tells you your battery supply voltage. Then your second voltage meter, voltage of the resistor, R, measures across here, like this, and that way you're measuring, this is your positive side of your resistor, this is your minus side of your resistor, and you're measuring the current flowing through that resistor. That gives you a tiny little voltage drop across it, which is measured by this voltage meter. And then your meter does a little bit of math to take the voltage drop and calculate the current. And that's where the current value that shows up on the screen comes from. So when this little meter displays, it will show you the voltage of the battery, it will show you the current flowing through that resistor, and it will calculate power, because power is voltage times current. So it can tell you how much power is being consumed by this entire circuit, because it's measuring the battery voltage, the voltage across the entire circuit, and it's measuring the current that goes through. A trolling motor, which is running at 12 volts DC, and it's drawing 50 amps of current, the power that it's pulling down is 12 times 50, which is 600 watts. Now, just for the fun of it, you can also calculate the power that's being lost to heat across just that resistor. We already know when you're running 100 amps through it, you're getting a 0.075 voltage drop across there. If you're running half of the current, which is what we will be running with the trolling motor that I have, which pulls 50 amps. So at 50 amps, you would be getting half of the voltage drop. So 0.075 divided by 2 is 0.0375 volts. And if you multiply 50 amps times 0.0375 volts, you get 1.875 watts. So if this thing was running at its fully rated power, the total power that's coming out of the battery would be 600 watts, and the amount that's lost in the meter itself is 1.875 watts. So in that case, 1.875 divided by 600 is 0.003125, which equals 0.3125%. So you're losing 0.3% of your power to the shunt resistor, which is almost nothing. These meters that you get, these cheap meters, are only accurate to like plus or minus 1% anyway. So a little bit of lost power to this does not affect the reading of the meter. It's down in the noise of the circuit. Now it's time to put this box together. When you do that, you can use the screws that came with the box, and I did confirm that these screws are stainless screws. They're not magnetic. So when I use this with salt water, I don't have to worry about these fasteners getting rusty. So if we real carefully tuck these wires in here, we should be able to install these screws. Give it a quick check with my battery. So there we go. It's reading 13.33 volts. No current, because there's no current running through it right now. And this 13 volts is after using this battery all evening yesterday evening. I haven't charged it back up yet. I think before I do charge it, I'm going to take it out and stick it in the kayak and do a quick function check out there too, and make sure that this is working properly. Looks pretty good. Here's our meter, and we have a couple of different options on how we hook this up. So let me pull out my controller box. So here is my motor controller, and this motor controller has a cable that comes from the battery here, and it also has a cable that goes to the motor. If I want to know how much power is coming out of the battery, I'm going to hook this meter up between the battery connector. So the battery is going to be my power in, and then power out, or load out, is going to go to the PWM controller. And now this display is going to tell me how much voltage the battery is supplying, which right now is 13.3, and then how much current is going to the PWM controller and the motor both. So when I turn it on, the power goes to 0, the power display, and then as I turn this up, say 25%, my voltage here is at 13.3, and the current is at 0.63 amps, and that is pulling 8 watts of power. And if I go up to 50% on my controller, there we go, I'm still only pulling 1.2 amps. And if I go full power, it pulls 2.6 amps. Now these numbers are with the propeller free spinning in air. If I was to go back there and load up that propeller, or if I was driving through the water and you were pushing the kayak through the water, then the current draw on the motor is going to be higher because it's actually going to be loaded. And that's what consumes power, real power, from your battery. If I just want to know what the power is going through the motor itself, not through the PWM, I could connect this meter on the output side of the PWM. So let's see what that's going to look like. So we're going to unplug it from the input side, connect these connectors back up, put the little safety lock in place, and now we're going to go to the motor side and unhook it. This is the cable going to the motor, so it's going to go on the output side of my meter. And this is the side that goes to the box, so it's going to go on the input side of the meter. And let's see what happens. With the meter hooked up to the output of the PWM controller, you're not going to get a reading on the screen of the meter until the voltage level coming out of the PWM is above a certain minimum level to power on the meter. So I'm going to put this right up to 50%. If I go to 50%, now it's reading about 6 volts off of the meter, which makes sense because 50% of 12 volts is 6 volts. Okay, looks like there's some sort of an alarm. Once you get below 6 volts, it starts blinking. 6.04, and there's 5.9, it blinks. So I'm not really going to be able to measure motor power only below 50% power output of the PWM controller. At 50% of the PWM controller, where it's 6 volts-ish and pulling 1.9 amps of current, and then if we bump it all the way up, we're at 13.6 volts and 2.4 amps. And the power draw here is 31 watts. And I don't remember what it was pulling at full power on the upstream side of the PWM controller, but the difference between the power into the PWM and the power out of the PWM is the efficiency of the PWM controller. And the more efficient it is, the closer those two numbers are going to be together. The less efficient it is, that means it's throwing away and losing power as heat in the electrical components in this box. And I know that there is significant heat generated when you drive this kayak at full power through the water. So I'm interested to see how much power is lost as heat. As soon as I can get out on the water, I'll start doing some videoing and compiling some data, and we can see how much power it takes to push my particular kayak through the water with my particular motor and prop setup.